Hello, everyone. Welcome to the DI 101 webinar series. My name is Jared Evans, and I'm the Director of Marketing for Distribution International. If you are new to the DI 101 webinar series, I'll let you know that it is an incredible resource offered to DI customers, partners, and associates. By partnering with our manufacturers and our industry experts, these webinars deliver informative presentations about industry trends, new technology, new products, and product applications. In order to fully support our customers, Distribution International offers products and solutions from multiple manufacturers and brands in many different product categories. This webinar does not represent an endorsement of one manufacturer or brand over another. We pride ourselves in partnering with manufacturers that deliver products of the highest quality to our customers. We are extremely excited today to welcome our strategic manufacturing partner, Owens Corning, for today's presentation. We welcome Doug Fast, who is a professional engineer and technical leader for Owens Corning. Doug has more than 20 years of experience in the insulation material industry, working in product testing, technical services, and new product development. He has a working knowledge of the materials such as foam plastics, fiberglass, and mineral wool, as well as other traditional high-temperature insulations. Doug has contributed to the industrial insulation industry through participation with ASTM, as well as technical education in the form of blogs and webinars such as this one, related to topics such as acoustics, corrosion under insulation, and personnel protection. We are proud to have Owens Corning present today, and we thank Doug for his time. We will field questions at the end of the webinar. To submit questions, please use the Questions tab on the GoToWebinar control panel. You can submit your questions at any point during the webinar, and we will answer the questions during the question period at the end of the presentation. Without further delay, I will turn this over to Doug Fast with Owens Corning.
Thank you, Jared, and thank you, Distribution International, for giving us the opportunity to present today. Good morning, everyone, and good afternoon, everyone. I hope this finds you well and that everybody is safe. Today we're going to talk about water resistance and industrial insulation. To start off with, just a quick promotion for Owens Corning. Owens Corning is a company that generates $7.1 billion in sales revenue as of 2020. They employ over 19,000 employees worldwide in 33 different countries. Owens Corning has been on the Fortune 500 list of companies for 66 consecutive years, and they serve the residential, commercial, and industrial markets. Now, to start off with, we're going to do a quick introduction. The first question is, why do we insulate? We're going to look at the impact of water intrusion from both a thermal and corrosion under insulation, or CUI, perspective. And we're going to talk about moisture intrusion and how does it happen. Next, we're going to talk about insulation systems design and material testing for moisture, which is something we don't always cover when we talk about CUI or system design. And then finally, we're going to end up with proper installation and also talk about the water-resistant mineral wool solution. So going forward, the basic question is, why do we even care about moisture and insulation? Now, best case, and this is a very short-term problem, but let's just suppose we get moisture in our insulation. The first thing that it does is it's going to degrade the thermal performance. And I always think of the analogy of if you're, say, swimming in the summertime and you're hot and you jump in the pool with your shirt on and you come out and your shirt's wet, you tend to feel much cooler until that water evaporates off your body, and then you start to warm up again. And that's because as that moisture is evaporating off your clothing, it's also removing heat as well. And it's also increasing heat transfer, which kind of helps keep you cool. But it's very worst if you have moisture in your insulation for an extended period of time. You not only have the effects of degraded thermal performance, but you also potentially create corrosion under insulation issues. So now you have that water under there for a long period of time, and corrosion is a chemical process, and the longer that process continues, particularly at elevated temperatures, the more transfer of electrons or more corrosion that you're going to have. So one of the proposed solutions is Owens Corning's Thermafiber Pro Section WR pipe sections, which are a water repellent insulation. Now, water repellency by itself isn't necessarily the cure for these things. It goes along with a system which we'll talk about in a little bit. But ideally, the best way to get the thermal performance that you designed into the system and to avoid corrosion under insulation is to keep the water out to begin with. Now, the first question is, why do we insulate? And, you know, I think when people say if there's corrosion under insulation, why don't we just remove the insulation? Yeah, you could do that, but the problem is that there's so much heat loss if you don't insulate something. So it's really a good idea, just both in terms of efficiency, cost, and also reducing greenhouse emissions that are coming off whatever power source that you're using, whether it be something like natural gas or electricity, you know, from a coal-fired plant or natural gas. So on the one hand, if you look at the image on the left, if we're insulating a cold pipe, what we're doing is we're just trying to keep the contents of that pipe cold as we transport it from point A to point B. So we insulate that to help heat from getting into that system. Now also because that's a cold pipe, moisture wants to condense on that cold pipe. So the only barrier between that cold pipe and the moisture that's in the ambient air is going to be either the insulation itself, like in the case of foam glass, which is pretty impermeable, or maybe use a fibrous insulation like fiberglass with a jacketing that goes over the top of it that helps prevent that moisture from going from the ambient condition and condensing on that cold pipe. And so if we're transporting this cold liquid, and say it's from a chiller to the thing that we're chilling, we can help to maintain that temperature, or at least reduce the rate that the heat enters that system as it gets from point A to point B. Conversely, if we have a hot pipe, what we're trying to do is we're trying to keep the heat in that pipe. So we're less concerned about moisture, but we add insulation because, number one, it takes a lot of energy to heat a pipe up to above ambient temperatures, particularly when you get up in the industrial region, up around 1200 degrees Fahrenheit. So we put insulation on to help hold that heat in. And then we put jacketing on the outside of that to help protect the insulation from the elements, because typically these processes will be outside or in an environment where you might be exposed to, could be anything, could be on the Gulf Coast, it could be animals, it could be hailstorms, it could be all kinds of things, but you just really want to protect that insulation system from the elements. But fundamentally, what we're doing with insulation is we're trying to keep things at a given temperature as we transport them from point A to point B. Now, before we talk about moisture and insulation, let's talk about the insulation system. And I know as an insulation manufacturer, we tend to have tunnel vision and only look at insulation, but really it's part of a much larger system, and this system has to work together. So if we're going from, let's say we go from the outside in and we start with the metal jacketing, as we talked about in the previous slide, we have that to help protect the insulation from the environment. And again, could be weather and could be forklifts, people, just anything in that environment that could potentially damage the insulation. We want to put jacketing between that to help protect it. An acoustical system, kind of going clockwise, we would have acoustic lagging, where we're just adding weight to that insulation system to help dampen that sound as it travels from the inside of the pipe to the ambient space. And of course, we have insulation. And for example, here we're going to say that it's there primarily for thermal reasons, although there's other reasons such as acoustical performance. In some cases, you might want to use it for fire, but fundamentally, you're using it for thermal reasons to help keep the contents of that pipe at temperature. Kind of working our way in, we might have an exterior pipe coating. And again, this is also an optional component. Probably a really good idea to, if you were in a operating range that's in that corrosion range, or where you might see a lot of moisture that could potentially get into that system. Finally, you have the piping itself, and again, this is going to range, it's typically going to be one of two things. It's either going to be plain carbon, which is fairly common, or possibly stainless steel in some applications that require more durability or more resistance to corrosion. Now, each one of these components has a specific role that it needs to play, and so one of the things you want to avoid is using a high compressive strength insulation to protect Owens 6 aluminum jacketing, and that's kind of false economy. The jacketing's role is to protect that insulation, not having a really tough insulation to protect the jacketing. The other part of using thin jacketing is jacketing does corrode over time, and thinner jacketing is going to corrode more quickly than a thicker jacketing. Now, the other thing is using corrosion inhibitors for insulations that absorb water. Really, you want to keep the water out of the insulation to begin with. Although if you do have an insulation that does absorb water, it is a good idea to have a corrosion inhibitor, but it's not a catch-all. You really want to keep the water out of the system to begin with, so that corrosion inhibitor doesn't need to be used. Then finally, there's coatings that make thermal performance claims. Anytime coatings are there to protect the pipe, there are some coatings that have been used that do reduce the surface temperature a little bit, but even just using a minimal thickness of insulation will provide more thermal benefit than a coating that you're going to apply that is pretty technical. You have to make sure you do adequate surface prep, make sure you coat properly. It does take a little more time as you wait for the subsequent layers to dry as you're doing it. So again, as you're looking at a system, you want all the components of the system to be correctly specified, installed, and maintained. We'll talk a little bit about maintenance later on, but it's something that we seem to forget about. Insulation is kind of out of sight, out of mind, so we don't think about it. But it is something we need to keep our eye on to make sure that we get the performance that we designed into that system. Now, looking at the impact of thermal performance, I think anecdotally everybody knows that this is what happens. That water is going to conduct more heat, and like the example that we had earlier. But if you look at water's thermal conductivity, it has 4 BTUs per inch per hour, square foot, Fahrenheit degree, which is about 15 to 20 times higher than what you would typically find with most common insulations, whether it's a foam plastic or fibrous or cellular glass. Now, whenever we introduce just a little bit of moisture into this, we are changing the thermal conductivity slightly. So as we add up to either 1%, 2%, or 3% of water by volume, we know that it impacts it. We look at the impact of thermal conductivity, but really, I think the answer is over here on the right-hand side. We have a system where, let's say we do add 1% moisture content, and it does impact our thermal conductivity. Even just adding 1%, we have a 23% increase in heat loss in terms of BTUs from that system, and we've increased our surface temperature 11 degrees. Now, as we go each subsequent step, as we go from 1 to 2 to 3 to 4%, we can see that surface temperature actually increases. And we're looking at what a 23-degree increase in temperature just of having wet or having insulation that has 4% moisture content. And we have a heat loss that's 51% higher than what we originally started with. So this is a real deal. And just because it's a little bit of water and we think, we have a hot system, it'll evaporate it off, it's a bit simplistic. Now, this particular example was done with just a 300-degree steam line, ambient temperature 70 degrees with no wind speed. And I know the jacketing here is aluminum, but the example that we used was actually more of like an all-surface jacket or kind of a white type jacketing. But anyway, it kind of shows the example of what the thermal impact of moisture in that system is. Again, if we had to tolerate that short term, maybe, but not something we want to live with for very long, because all that equipment that we've sized to anticipating a heat loss of about 300 BTUs per hour per foot, and all of a sudden we're dealing with 50% more than that, we're going to have a hard time with that equipment keeping up. So then that's going to create other problems. Now, the other part of this, and this is the one that we probably talk about most in the industry, is corrosion risk or COI risk. And there's just a couple of things to think about here. Now, there's a lot of things that impact corrosion risk, and number one is, probably the biggest one is temperature. So if we look at this table down below, and if you look at painted pipework that's less than 10 years old, and continuous operation, I think that's the operative word there, is continuous operation. You see that if we're operating our equipment continuously, pretty much outside of that high risk zone, so that's going to be 86 degrees and below or 248 degrees and above, there's really a pretty low risk of, or a much lowered risk of corrosion underneath insulation. However, if you look at that 86 to 248 degree range, that's the range where you have enough heat there to actually keep that water warm, where you're kind of driving that reaction rate that we talked about, but not enough to fully evaporate that water off of the system. So you basically have a hot, wet condition, and that, of course, is going to facilitate any kind of corrosion activity that you have going on there. So even as we move over to the next section where we look at intermittent operation, we are increasing our risk a little bit more. However, we're going basically from low to medium in most cases. But again, we still have that temperature range from 86 to 248 degrees. That's really the critical factor here. And then, you know, as you get to older equipment, things like that, you can see our risk is now from medium to high. So really, the takeaway from this is if we're going to be in that 86 to 248 degree range, we have to make sure that we keep that system dry, because we just don't have enough energy to get rid of that moisture that's in the system. Particularly if we have an older system, we want to be mindful of that. And if possible, if we're going to be in that range, we really want to consider using a coating to help protect against corrosion, to at least help mitigate that problem. So again, the impact of corrosion, just to talk about it, and this is only one slide for those of you that have seen too many CY slides. Corrosion's expensive. What happens is we have moisture that gets into our system because of any of these items below: rainwater, flooding, pressurized cleaning, you know, wind-driven rain, a lot of times vapor penetration into the system. So there's a lot of ways that moisture can get in. You can never make it completely vapor tight, at least on a high temperature application. If you're doing low temperature, then you have to pay particular attention to detailing there. Hotter systems are a little more forgiving that way. We also have some other things we have to consider too, things like chemical exposures for both acids and bases, and salts. And maybe just one word here. I think a lot of times we tend to think of rainwater as being distilled water, not containing any chlorides. However, depending on where you're located, and depending on what kind of water you have available, you might have water intrusion from a freshwater source, but it actually contains chlorides. So any chlorides that are in the ambient air are going to get into your system. Even though we have tests, corrosion tests that look at taking distilled water going through that insulation down to that pipe surface, they're using distilled water in that test. So if you're taking rainwater or water that has chlorides in it, and you're adding that onto there, your corrosion rate is going to be much higher. So again, another good reason you want to keep moisture out of your system. And again, looking at that temperature bar along the bottom, you can see that again in that 86 to 240 degrees is kind of that sweet spot. However, the 240 degree part is optimal. That's where you're going to find, again, it's hot enough that you have this hot, wet condition. You're trying to dry that water off, but it's still going to be hot and wet. And it's really going to facilitate that chemical reaction, create a lot of corrosion problems. Now, again, how does it get in? We talked about some of the sources, but here are some of the things that we see in real life. So if you look at the image on the left, you can see we either have damaged or missing jacketing. And I think a lot of times somebody looking at that at a glance might think, oh, it's on a hot system, so the water will just boil off, so we don't really need to put jacketing on there. But, you know, once that gets saturated, you know, you start having those problems that we just talked about. Maybe you have poor detailing, like you see in the center picture here, where they've actually just cut a gap in there. So unless that is protected from the elements or from any water sources, that's a prime entry port for moisture to get into that system. And finally, on the right-hand side, if you look, this jacketing job looks like it was done really well. The only problem is they put that seam right on top. For those of you that live in areas where there's snow, we know that snow will accumulate on the top of those types of systems, and water will actually wick between those two layers and infiltrate into the system. We always want that overlap to be usually at that 9 or 3 o'clock position with that flap facing down, so it sheds water away from that system rather than being up on top. But anyway, those are things we commonly see. Now this one I think kind of tells it all. If you look at the topmost arrow, you see there's some discoloration there. So who knows what's going on there, but maybe it's getting some oil that's on top of it, which might be protecting it, or it could be something corrosive that's actually eating through that jacketing. You know, we don't know. It is a symbol that there's a leak somewhere. If we look over on the arrow on the left-hand center side, again, we see another lap that's on top. And again, we know the reasons why we don't want that to happen. But I think more telling is this pipe that's closer to us, the larger one. You see the large oval and that bottom arrow. You can see that there's actually cuts in that jacketing. And earlier I was talking about the Owens jacketing that you have over a heavier insulation. Well, this is the reason why that thinking doesn't work here, is because this jacketing is supposed to be protecting the insulation. Clearly, there's been some kind of traffic or damage or something that's happened here. So now we've created all these entry points for moisture to get in. So again, this is either worker traffic or just disregard for this entire system. So there's a lot of potential sites for moisture to get in. Now, when we talk about insulation and water repellency, or how you design for moisture intrusion, there's usually three different ways that this is done, and these usually are driven by insulation types. One theory is that you use water repellency, and water repellency just keeps the water out. It just sheds the water away. That one seems to make the most sense. If it never gets towards the middle of the pipe, then you've done your job. The other theory is to use corrosion inhibitors. So if you have an insulation that might absorb more water, maybe you want to have something that has a corrosion inhibitor in it. So at least if any moisture does get into that system, at least it reduces the corrosion potential for that down to something like deionized water. So it's going to reduce that rate dramatically. The only challenge with that is that even though you have all that water there and that corrosion inhibitor to help mitigate that corrosion part of that, you still have that impact of the lower thermal performance because the insulation is just going to conduct a lot more heat through that wet segment. And then finally, we have our third theory, which is a combination of both, where you have water repellency and corrosion inhibitors. And that seems to make a lot of sense too. And some material types actually do this, where you keep that water out and you also reduce the corrosion potential if you have any water that gets in. One thing to note here, though, and this is going to covers pretty much all insulation types, is that waterproofing agents will oxidize above 600 degrees, and this is regardless of what insulation type it is, with one exception. Foam glass, because it's impermeable to water vapor transmission and liquid water, it will keep its water repellent properties up to its 900 degree maximum use temperature. But otherwise, these other additives that are used with these other products for water repellency will burn off at about 600 degrees Fahrenheit. Now, I think looking at all of these, and we see all three of these in the marketplace, I always come back to this statement at the very bottom made by NACE in their technical paper, the SP0198 paper that's out there, is that because CY is a product of wet metal exposure duration, the insulation holds the least amount of water and dries most quickly should result in the least amount of corrosion damage to equipment. So to me, and again, the best way to deal with these problems is to keep moisture out of the insulation to begin with. So when we talk about moisture testing, and this is something that we don't talk about, we always talk about corrosion results and how they work with different insulation types and different corrosion tests. But there's other moisture tests that go along with these material types. These are the four that you see over here on the left-hand side of the page. One of them is water vapor sorption. This is how much water actually clings to the surface of the insulating material. And this is typically done with things like mineral wool, fiberglass, and aerogel blankets. So we're just looking at, so basically we take the product, we put it in a humidity cabinet with high temperature and high humidity for 96 hours, and then we weigh it once it comes out. And generally speaking, those numbers are pretty small for the products that are tested. For fibrous materials, it's going to be less than 5% by weight. Another thing that we look at is water vapor transmission. And although you won't have an insulation type that has this requirement, you'll see this associated with insulation facings. One of the reasons we care about this is if you look at a facing, it's usually going to have a very low perm rating because you don't want a lot of moisture going into that system if you have a chilled water line. Now, the other part about this is that the higher the perm rating, the faster the insulation will dry if it does get wet, because water vapor can more easily pass through something that has a higher perm rating. It's about how much the amount of moisture that will pass through something in a given period of time. Then we have something that's new to the market is water wicking, and you'll see this with mineral wool is what you've seen it with, and there's some other insulation types that have tested this as well. But you're looking at essentially this test is mimicking leaving the insulation outside and it's exposed to the elements. How much water is it going to wick into the material? So essentially, we're just putting a section of material into a bath of water that's 20 millimeters deep, and that's about 5/8 of an inch to 3/4 of an inch. And we're going to measure, we're taking the weight before and after to determine how much how much water is wicked up into that material. And again, you'll see that as a not a formal ASTM requirement, but something that's shown up in the industry, particularly around mineral wool pipe sections. And then finally, you have a submersion test, and this is where you put the product itself underwater for a given period of time. You do a weight before and a weight after, and you determine how much weight it's picked up, typically as a percentage. So we go over here to this table on the lower right-hand side. You look at water vapor sorption; those are going to be more around fibrous insulations. Water vapor transmission, and again, these aren't typically tested, although cellular glass is going to have that in their spec because that is one of the properties that is most important with that product. And just to point out the two extremes, you have mineral wool, which is very vapor open, versus cellular glass, which is very vapor closed, which makes it a great product for use in cryogenic and cold applications. And if you look at calcium perlite and aerogel, they're still considered to be vapor open, although maybe not as vapor open as mineral wool, but they will allow water vapor to pass through those products. Wicking for pipe sections, you'll see that the metric there is it will only absorb 1 kilogram per square meter. So, if you can imagine, that's essentially 2.2 pounds over roughly a 3 foot by 3 foot section, which isn't a lot of water. So, and again, not an ASTM requirement, but something you see in industry, but again, not required of the other insulation types. If you look at shipped water content, interestingly enough, calcium silicate insulation has an ASTM requirement that it can have more than 20% moisture content as received or as shipped, I guess. So that's how that addresses moisture. Submersion methods, if you go down to look at ASTM C240, which relates to foam to cellular glass, and that's going to be 0.5%. And because it's a glass product, it's just not going to absorb any water. Really, the only water absorbs is whatever surface contact or surface tension it has that stays on that surface. So those numbers are really low. You look at something like aerogel, and it can be as high as 16% moisture content. And again, that's after it's been heated to 600 degrees Fahrenheit. Because remember, we don't have any waterproof insulations with the exception of cellular glass above 600 degrees. Now, prior to putting that in, conditioning it, that requirement would be more like 8%. Then finally, submersion. And again, this is going to ASTM C610, that's for expanded perlite. That's going to have, that allows it to 50% moisture content. But again, that's after heating to 600 degrees Fahrenheit, and that's after it's been, heated and soaked for long periods of time. So again, none of these products are going to be waterproof at those temperatures. But the thing to keep in mind is the only part of that product, if we're talking a pipe section or even a board, is going to be next to that hot surface. So you might not be water repellent maybe a quarter or halfway through the product, but that outside the product is still going to be water repellent because that outer portion of the product has not seen those temperatures. Now, one of the benefits of mineral wool or a case for mineral wool is that, you have the water repellency helps to keep the water out. And because, as we saw, I always hate the word breathable, but when we talk about water vapor and perm ratings, things like that, that's the ability of that water vapor to pass into and out of the product. So water can very easily get out of that system if it does get into that system due to leakage. It's also low density so it won't hold as much water. So imagine if your product holds 100% moisture content. Well, you'd rather have a lighter product than a heavier product. If you have an 8-pound product, maybe have 8 pounds of water in it. If you have a 15-pound product and 100% moisture content, you're going to have 15 pounds in there. So the less water you have, the less you have to drive on or try and remove from that system. And then finally, mineral has low shrinkage. So the advantage to that is as you heat it up, those joints don't shrink and you don't create these gaps where moisture can actually go in and bypass the insulation. But again, best way to prevent corrosion is to keep water out of the system in the first place. And again, we want to fix the problem and not the symptom. So here's the slide. I guess that we're promoting the product here, and this would be the Thermafiber Pro Section WR pipe insulation. Now, even though there's a great story here to tell here about water resistance, there's also some other good things about it as well. We have a lot of acoustic information on this product. Comes in a longer length for productivity, but that's for a different webinar. The point is that we have water repellency to 572 degrees Fahrenheit, which is the best in class and highest temperature water repellency in the market. It also has the lowest amount of water wicking into the product in the marketplace. So if you see that plot down below, you can see that those requirements of 1 kilogram per square meter that we talked about earlier. And then you see the next closest competitor, and then finally our product at the bottom, you can see it's significantly lower. And again, because mineral wool is vapor permeable, it will dry quickly if it gets wet. It's lightweight, and doesn't have an impact on coating adhesion. And that's something that we'll talk about in the next slide. But that is also something that is out there that could potentially influence your decision. Now, we have information on our website regarding not only the brochure for the Pro Section WR product, we also have a technical bulletin on water repellency that talks about the wicking method, submersion, also talks about the impact on coating adhesion as well. So it gives the whole story of how our water repellency works, and as well as the adjacent topic of coating adhesion. So what is it about coating adhesion? One of the things that you'll see in specs is there'll sometimes be a requirement that the waterproofing agent will not impact or contain silicones that could impact the potential for coatings to bond to a substrate. And usually that's a coating you would apply to a pipe, probably a carbon steel pipe. Now, one of the problems is when you use a silicone and you spray it on the surface, or use it on the surface of your insulation, it can also impact the way that pipe coating is going to bond to that pipe. And what you'll see is these little pinholes where that coating doesn't flow properly over the surface of the pipe. So one of the ways that they test for this, they use the VW 3.10.72 that's been referenced in the marketplace. What they'll do is they'll take a sample of this insulation, they'll scrub it across the surface of carbon steel, and then they'll coat that piece of carbon steel, and then they'll look for defects. And what they're looking for is those little pinholes that we just talked about. Or they'll take a piece of carbon steel, they'll put insulation on top of it, they'll pour solvent through the insulation, and then allow it to sit, the insulation to sit in that solvent for 10 seconds before they remove it. They'll allow it to dry, and then they'll coat it, and again, they'll look for those defects. So kind of depending on which method you use could have an impact on whether your waterproofing agent is going to impact the ability to coat something. Now, what this new VDMA test does is it essentially looked at this previous method and thought, well, why don't we just combine two so we don't have to specify whether we did this dry method or the solvent method. And the VDMA method it's pretty extensive, and so there's more details in our technical bulletin. But for the test that was used for this comparison, it was just simply combining both, where you're actually scrubbing the insulation across the surface of the carbon steel in solvent to make sure that any agent that is in that insulation is going to be released and dissolved into that solvent. You allow it to dry, and then you coat it, and then look for defects. And so, of course, we've done that with our product, and provides and the results of that is that our product can be used in spaces where they are applying coatings, and our product can actually be in contact with the equipment being coated and the equipment that's being used to do the coating. So you won't have any impact or negative effects if you're using our product in an atmosphere where you're going to be coating as well. Now, so that's the insulation part of this. The other part of this is we talked about this earlier, you want to make sure you properly select and install the insulation material and the insulation system. You always want to make sure that you're sealing along longitudinal and circumferential joints. You want to shingle joints like we talked about earlier, and there's an example of this over on the right-hand side. If you see between the correct and incorrect, if that water drop falls on top, it's going to shed off that lip that's on the left or on the right-hand side. Whereas if you look at the image on the right, you can see that water droplet is going to go right into the jacketing and then right into the insulation system. Another recommendation would be to use drainage holes in the underside of insulation when possible. And again, this is only for a hot system. You do not want to do that for a cold system. But if you do have an area that could potentially accumulate moisture, that's certainly a consideration. We talked about this earlier, but using thicker jacketing in high traffic areas certainly makes sense, and it's a lot cheaper than having to replace insulation or having to go back and remediate a section that's been affected by CY because of the jacketing and been damaged. You want to use the proper jacketing. GRP claddings, glass reinforced plastic, those work really well. They're flexible. They provide a lot of durability, and that might be something for you to consider. And again, we talked about coatings, but again, if you're in that danger zone, they should very much be a consideration. Not that we're a coating manufacturer, but certainly there's a lot of good coatings out there and some manufacturers that have some products that could certainly address your needs. Then finally, over in the low right-hand side, there's aluminum jacketing thickness, and this is created by ASTM. And again, this is a good process, a good chart to follow or recommendations to follow. These should be considered minimums, and of course, there's nothing wrong with going thicker in high traffic areas or even double layering. Again, you want to protect the insulation system from damage. The other part of that too is as you step on it, you kink it, you do these other things, and you not only can fracture the insulation underneath, but also create gaps where water can get in. Final part of this, and again, I think this has been overlooked until recently. You not only want to properly design it, you also want to make sure that you maintain it. And I think this is where a lot of it goes wrong. Over time, we know that metal, whether we're using aluminum or stainless steel, is going to expand and contract, and it's going to create gaps. And I know insulation is typically out of sight, out of mind, but it's something that we have to keep our eye on. And if you're developing an inspection program, you always want to find out what those high risk spots are, and you're going to monitor those more closely than maybe some of the lower risk parts or maybe some of the newer parts. But you should have a plan in place and a schedule for checking to make sure that these things are remediated before they get to be large problems. Now, this one I always look at, and if you're looking at this diagram over here on the right, I always have to remind myself. I always think in terms of straight sections, but again, real world piping systems have a lot of different details and hurdles to try and create the system. So it's not easy to do. You have elbows and penetrations. You have shoes, pipe racks, terminations, a lot of different things that you have to seal up as best you can to make sure that moisture doesn't get in. I think the interesting thing is API, NACE, CINE, they all have the same recommendation that you're always going to want to look at those possible entry points and make sure that those are flashed, caulked, sealed, in any way possible. And to borrow from our roofing folks, I think you always want to think like the rainstorm or the water drop is, how am I going to get into this system, and try and figure out ways to shed water, try and figure out ways to avoid having standing water, and just how to keep that moisture out of your system. Sometimes it requires a little bit of design attention and making sure that it's installed correctly, but that time spent up front is certainly worth the value that you're putting, the system, that value that system will have if it's installed and maintained properly. So to kind of sum everything up, we always want to design things to keep the water out, but we have to assume that it gets in, and we're going to have to think about how is that going to get out if it does get in. Want to make sure that want to consider drain holes in above ambient conditions. Use water repellent insulation where appropriate, because again, you want to shed that water away before it even gets close to your pipe, and that's the best ways to keep it out to begin with. And you don't want it to absorb into the insulation, because then you have that problem with the increased energy usage of that system. You want to make sure that the insulation is installed properly and that you got the right installation on your job. And again, you want to inspect and maintain that system. And again, for the water repellent insulation part of that, we have our Thermafiber Pro Section, which we talked about earlier. Now, to kind of wrap everything up, we've talked about a lot today. There's a lot of additional resources that are out there, and two that I would point out. One would be NIA. They have a lot of information and training available for not only energy appraisal programs, but they also have training programs for insulation inspection, specification. They have specification guides, they have material charts, they have calculators for probably everything that you would want to do. There's a lot of content there as well on different topics, things like CUI, personal protection, just materials, things like that. So it's a great resource for you as you design and specify and assemble these things. The other part of this would be our NAMA 3E Plus software. It's free and it's on our website. The link's here. You can also go to the industrial portion. It'll be on that page as well. But 3E Plus is a great tool if you're looking at trying to determine your safe to touch temperature, which is the software that I used in that earlier example we had about how we increase the temperature. But it can also be used for figuring out the thickness of insulation you need to avoid condensation on that pipe if it's a chilled water system. There's a lot of things that you can do with it, or if you're using different material types, you can always figure out what combination can work if you have, it's kind of a strange configuration, but it's a great tool, pretty commonly used and easy to use. I highly recommend it. Then we also have Owens Corning resources. Again, I invite you to visit our website and see the product offering that we have. They're all tremendous products, I think. And a lot of information there as well, which would include our ebooks, guides. There's also guide specs, user manuals, things like that. So there's a lot of information there. And of course, if you don't find what you're looking for, you can always give me a call and I'd be happy to talk with you. Here's my contact information. So that's all I had for today. I really want to thank you for your time and attention today. I know this isn't the maybe the coolest subject to talk about, but I think it's something overlooked and certainly interesting to me. So with that, I'll turn it over to Jared. I don't know if we have any questions or not, but again, thanks for your time.
Thanks, Doug. Appreciate that. That's very informative. Just a reminder, to submit questions, use the questions tab in your go-to webinar control panel, and you can type out the question and submit it. While we are waiting for questions, I do want to take just a quick second to tell everyone about our new digital customer platform. Last year, we at Distribution International completely overhauled our website, distributioninternational.com. We added a wide range of value-added features, including our customer portal that we call Customer Connect. You can view past invoices, request quotes, and even submit orders all online. And maybe the best feature is a detailed online product catalog of more than 27,000 products that is easy to search and easy to navigate. Go to distributioninternational.com today and register for your online account to make your job easier. All righty, let's see what we have for questions. The first one is from Kenneth. He says, you talked about steam systems and water systems between 84 and 248 degrees. Is there a different range for insulating animal oil pipes of 80 grade carbon pipe?
Just so I understand that, are there differences between going with different wall thicknesses of pipe, like going between 40 and schedule 80?
It does not specify. Let's see. Kenneth, see if you can provide some more clarification there, and we'll come back to you. Let's see. For the next question is for EN13472 wicking test method. What is the size of the tested pipe section to be placed in the 20 millimeter deep water?
Yeah, that's a good question. And I hate the answer. Okay, so it depends. But what they do is there's a formula that's in that standard, and so what you do is it has to do with the size of the pipe, and so of course if you have a smaller diameter pipe, your piece is going to be longer than if you had a larger diameter. So what the standard says is that you have to have 40,000 square millimeters, which is roughly like in roughly 8 by 8 section is what you're trying to submerge, and so you just have to adjust the length of your pipe section to make sure that you have that area. So you can't gain that test by using a smaller diameter pipe section. So I don't know if that answers your question or not, but that's how they try and make sure that there's an equivalent length to get that area to get the correct area submerged.
We got some clarification from Kenneth. He says, back on that first question, he said, we just use 80, but that's just to be standard. The question is more between the difference between oil and water.
Oh, okay. So whether it's oil or water, the insulation doesn't know what's in the pipe. So so if it's 300 degree oil, 300 degree steam, it's as far as the outside of the pipe is concerned, it's just 300 degrees. So that shouldn't make any difference. You're just insulating for temperature and not so much for the contents of the pipe. I think. I hope I got that answer right, or I hope that answered your question. I'm not sure I did.
And he follows that up, Kenneth follows that up just asking, so temperature should not matter. Is that correct?
Temperature, yeah, it doesn't matter what's in the pipe. The only thing you're thinking about is temperature.
Okay. All righty. That's all the questions we have. Thank everybody so much for joining us today. Doug, thank you for taking your time to present. If you have any questions about anything that was discussed today, you have Doug's information there on the screen. And you can also reach out to your Distribution International representative, and we would be happy to help. I do want to remind everybody to follow us on LinkedIn and go subscribe to our YouTube channel. We record all these webinars, and post them on our YouTube channel, so you can go there and view past webinars that have great content and great value-added content there. So go check that out, and go to distributioninternational.com. Everybody stay safe, and thanks for joining. Y'all enjoy the rest of your week.
Thank you, everybody. Have a great week.